Hello, everyone. We are still missing the moderator of this session, but we will start by introducing the speakers shortly. So, Nienke, as you are the first speaker today, perhaps you could share a few words about yourself.
My name is Nienke Koeman, and I am working at KWR, which is a Water Research Institute in the Netherlands. And I'm in the water treatment team. KWR is researching the whole water cycle. And my presentation will be about the reuse of activated carbon. Are there already people attending, or can we see that?
Yes, there are indeed 29 people in the session at the moment. So welcome everybody. We're going to start off with Nienke's presentation, which she just introduced herself. And then Kees is the next speaker. And after that, Shara will follow. And then the last speaker would be Jim. So please welcome, and a special welcome to Nienke. Thank you.
Okay, I think I'll just start. Welcome everyone. The title of my presentation is called Reuse of Activated Carbon for the Removal of Organic Micropollutants. So OMP is organic micropollutants. And I present results from a project which is in cooperation with different partners, both drinking water companies and water boards, Aqua Minerals, and KWR Water Technology. Next slide, please. So what we see is that organic micropollutants in wastewater are getting more and more attention, and they have to be removed. And it is already shown that the use of powdered activated carbon, so PAC, in wastewater treatment is a good way to remove these OMPs. It's very effective, however, it's not very sustainable. What we also see is that activated carbon is used in many different places, also with different aims. For example, Dinea, which is a drinking water company, they use PAC in the production of drinking water and mainly to remove color. And also Friesland Campina is using PAC, and they have lactate production, and there they also use PAC. And this PAC may still have some capacity to remove other types of components. And the idea of this project was that we can maybe remove that carbon in the wastewater treatment, and that can be more sustainable. Next slide, please. So first we have to find out whether this activated carbon a suitable source is to use in wastewater treatment. And therefore, we have to look at the technical and economical feasibility, and also whether other things are possible, like transport. So first, we try to answer some questions. For example, what is the absorption capacity? Should we dose after the normal, as a polishing step after the wastewater treatment? Or should we dose it in the sludge line? Can we expect problems with other components because it's already used the carbon, so there are some components absorbed, but they may desorb again. Can we expect problems there? What is the concentration of the activated carbon in the slurry, and does that vary a lot from the different sources or per source in the time? We have to look at transport, for example, for distance, for costs, what are the available volumes, and we will perform a life cycle analysis. And next slide, please. So we started with the absorption in effluent. So as a polishing step, and we also looked at wastewater from horticulture, and there is some standardized water that is used a lot for horticulture research in the Netherlands, and it contains a mixture of 11 crop protection agents. And what we saw is that if we use the activated carbon from Guinea, we could remove all those components, and the correlation is very good for all the different components that we tested for this whole mixture. And what you see is if we add more activated carbon, the concentration goes down to very low concentrations. And the aim is to remove at least 99% of each crop protection agent. And that works if we use this Guinea carbon. And next slide, please. Of course, we want to know how this Guinea carbon relates to other carbon sources. So we compare it with fresh carbon sources to remove 95% of the individual components. And then if we look at this table, can you see my arrow? If we look at the table in the column in the middle, what we see is that the minimum amount of activated carbon that is required to remove 95% of all the crop protection agents is that we need 50 grams per cubic meter of this Guinea carbon slurry. And we compared it with 4 different types of other carbons, which are fresh. And we see that for the other carbons, actually, we need more. And that is because the carbon which is used in drinking water production has a very high loading capacity. And it's already replaced when there is only, when not so much is absorbed yet. So we see that not so much is required, only 50 grams per cubic meter of carbon. But this carbon is, of course, in a slurry which contains also some other dry matter, for example, sand and carbonate. So about 27% of the dry weight is carbon. So we need 185 grams per cubic meter of dry matter, which is also very comparable to if you use fresh carbon. Next slide, please. We also looked at other types of components, and we used a mixture of components that is used in the Netherlands for wastewater treatment research, and it's a mixture of about 19 but it's a mixture of 19 components, of which most are medicines. And to see what we wanted to do is fight the effluent with this mixture of components to guarantee that they are present in the effluent. And we wanted to add representative concentrations. So we looked into data from wastewater treatment plants, what the concentrations could be. And the target is about 70% removal. And next slide, please. So what we did is we dosed the activated carbon in effluent, and so this is as a polishing step. And the tables are very small. If we dose about 10 milligram or 15 milligram per liter, we can remove 6 components by 70%. If we dose 20 milligram per liter of fresh carbon, we remove about 15 components by 70%. If we look at the second table, we see that Guinea carbon, if we add about 20 milligram per liter, we remove 13 components by 70%. So which means that the amount which we need to add to remove 13 or 15 components by more than 70% is more or less the same if we compare the Guinea activated carbon with fresh activated carbon. And this fresh carbon which we use is by the supplier, it said it's suitable for use in wastewater. We also looked at the carbon from Friesland Campina, so from the lactate production, and there we saw that there was very little absorption capacity left. So I didn't show a table. What we see in both the fresh carbon and the Dunea carbon is that the same components that absorb very little, and the same components absorb very well. So, for example, gabapentina is the lowest line in both graphs, and propanolol is the highest line in both graphs. So, which is of course not strange, but yeah, it shows us that the system works. Next slide, please. Maybe you can click once more. There's a picture. So what we also want to look at is, instead of dosing it as a polishing step, is whether we can dose it in the activated sludge system. So for that we did bioreactor tests, and we used the bioreactor in a sequencing batch mode, so that it's comparable to a wastewater treatment plant. And what we did with the Dunea carbon is that we dose it at the end of the aeration period, like about 5 or 10 minutes before that period ends, because during the aeration period, most of the readily degradable biomass is degraded, and then there is OMPs left, and that can absorb. Well, if we would dose it directly in the beginning, it's probably directly absorbing all the readily biodegradable organics, and we don't want that. So we will see whether that's a good option. For Friesland Campina, we saw that polishing is not an option at all, and what we hope actually is that there is vitamins and lactose absorbed on the carbon, and what we hope is that when this carbon is being recirculated in the system together with the sludge, and it has a sludge retention time between 14 and 22 days, depending on which wastewater treatment plant you're looking at, we hope that it's sort of regenerated. It's still really a question whether it works, but we can see maybe it works or not. Next slide, please. Furthermore, what we will look at is other components. For example, we know with the Dunea carbon that there is PFAS present, so we have to see whether this PFAS will desorb. And maybe there are some other components that can pose problems. We don't foresee them yet, but they may come up. What we also look at is the concentration. The Dunea carbon is only 4.7% of the stream, and 83% of the stream is water. So we have to see where in the process we can take actually this activated carbon, because maybe there are also places with a lower water content, or maybe this high water content has some advantage. So we have to look at that. With Friesland Campina, there are different locations. So there's location of Veghel. It contains about 13% of activated carbon. There's also another location in Borculo, and it's more or less the same. And we also have to look at the availability. The carbon that is available from Dunea is only suitable for maybe 2 or 3 wastewater treatment plants in the Netherlands, if you look at what they need for a whole year. Well, for Friesland Campina, they can probably supply to all wastewater treatment plants in the Netherlands if they see this as a good option. So the availability is also a very important thing to look at. Next slide, please. So the conclusion is that there are different sources of activated carbon, and this activated carbon from Dunea has a very high absorption capacity, so it's very suitable to use in the wastewater treatment plant. However, the availability might be limited. For Friesland Campina, there is a regeneration required, and we don't know yet whether this is possible. However, the availability is abundant, so if it's possible, it's going to be a really good source. And at this moment, we are still in the middle of the research, but we think it's very promising. Next slide, please. Okay, so this research is performed by different people from KWR, who I'd also like to thank, Frank Oosterholt and Julia Monjusera. And I would like to thank all of you for my presentation. If you have any question, please put them in the Q&A. Thank you.
Andre, are you here? Yes, thank you. Perfect.
Okay, can you hear me?
Yes, perfectly well, thank you.
Okay, thank you. And maybe you can see me as well. Nienke, what do you foresee will be the next steps for you to in this project?
So what we're working on now are these bioreactor experiments to see whether it's possible to dose the carbon in the sludge line. And what we will also do is look at all kind of more operational details. So how we should transport it, what the sort of distance is that we can transport to make it still economically feasible, but also technical feasibility. For example, what we see is that there is it's a very water resource, and that has an advantage because you don't there is no danger for explosion, while this danger is there when you use fresh carbon. What we will also do is a life cycle analysis, so we still have some steps to go to be able to draw a very good conclusion, but the first results are very promising.
Thank you very much, Nienke. I hope you are making steps, because I think from the sustainability aspect, I think these are very important steps you make. Good luck with the next steps. If you're okay with this, I would like to go to the next presenter. The next presenter is Kees Roest from KWR. Kees is a senior researcher at KWR, but maybe you can introduce yourself better than I can. Your focus is on the Circular Water 2020, if I'm right, the impact and opportunities of a fully circular urban water cycle. I think very interesting aspects you will show us, and hopefully we can learn something from it, and maybe it gives some opportunities for the listeners as well. Kees, go ahead.
Thank you, Andre. Yeah, I hope it gives inspiration. So let's continue with the next slide. And then I start my presentation about Circular Water 2050, so the near future. And indeed about impact and opportunities for a fully circular urban water cycle, which is a study we are still performing, but we did already a lot together with the drinking water companies in the Netherlands and the Watergroep in Flanders. Also partly financed by STOA of the water authorities in the Netherlands. Aqua Minerals, also mentioned in the previous presentation by Nienke, is joining this project. They are responsible for resource reuse of side products from drinking water and wastewater treatment, and Energy and Resource Factory, which is a sort of consortium from the Dutch water authorities, also speaking about resource recovery and reuse of wastewater side products. Next slide, please. Very short, Andre introduced myself. So I'm working at KWR as senior scientific researcher, and I also do some program management of water technology and industrial fluids processing. Next slide, please. And the presentation I give is part of the joint research program Water in the Circular Economy, which has a focus on closing the water cycle, but not only the water itself, but also other components, and to do this in a safe and healthy way. So combining feed, food, water, health, and all other components and aspects that are needed for circularity in the urban water cycle. Next slide, please. And why do we focus on 2050? Besides, it's a nice number, 2050, but also because it's the aim of the Dutch government to be fully circular in 2050, which sounds maybe far away, but it's already very soon, because less than 30 years from now, we are in beyond 2050. So there's not a lot of time to make a transition to circularity. And before you make this transition, you also have to define how the circularity looks like in 2050. So that are aspects that we investigated in this project, Circular Water 2050. Next slide, please. Because we have to transition from linearity, water use, energy use, resources, to circularity, so to reuse. But that's sounds easy maybe, but it's more complex and involves a lot of aspects that need to be investigated. Next slide, please. So what we did is 3 activities focusing on the resources that are used in water treatment, so drinking water treatment and also wastewater treatment, but also the sources that are produced when you are treating this water. And these components need to be circular. So the components you use need to be from circular resources, and the components you produce or potentially produce can be also reused for circularity. And the example about activated carbon in the previous presentation is very interesting, because that's also part of the components you use for treatment and then can be reused, and in that case even in the water cycle itself. The second point I will pay some more attention in the next slide. So we defined and made a nice, I think a nice picture of the fully circular water cycle, water chain in 2050. And at the moment we are still working on activity 3, defining measures and actions that are required to reach that circularity in 2050. Next slide, please. Next, yeah. If you work on circular economy, it's good to have a definition. And actually, we adopted an existing definition of the Social and Economic Council of the Netherlands, because it fits very well with our thoughts of the water sector. And it not only defines the reuse of materials, so making materials like energy and water itself and other components circular, but also in a socially responsible manner within the ecological preconditions. Because if you recycle components, you have to do this in a very safe way for the people and the environment. Next slide, please. Next, please. So we also made use of the donut economy and the picture that is depicted here, which includes an ecological ceiling and a social foundation. And I will go quickly to the next slide, because we translated this to the water sector. So the energy and material flows, and the water is one of the materials. They are the ecological ceiling and the social foundation that are value for people, like health and well-being, which is further depicted in the next slide, please. So we translated to 16 characteristics which are used for these ecological ceiling and social foundation. I hope you can hear me, because I see in the chat Saskia doesn't hear me, but I hope others can still hear me. I see Andre. Okay, yeah, thanks. I will continue. So in the social foundation, we have aspects as public health and safety, comfort. So if you are going to reuse components, it can be that there are also contaminants in these components. So it's important that these contaminants are removed and that the components can be utilized in a safe and responsible way. So that's why we have these nice 16 characteristics which can be used as a sort of dashboard to check a circularity of new concepts. Next slide, please. So what we did, we gathered several people together to discuss circularity in 2050. So we made drawings of 2050 and technologies that can be implemented in 2050 for circularity. And all these drawings and input of people from the sector and closely to the sector or outside of the sector, we combined to a general picture in the next slide, if it's correct. So this slide depicts a Dutch city and some smaller cities on the background, also agriculture, so a situation in the Netherlands, which looks pretty much as it is now on the first side. But in the picture, there are a lot of examples and inspiration for circularity or possible circularity in 2050. So there is a lot of recovery of materials, a lot of blue-green roofs to keep rainwater a bit longer in the city and to have also a cooling effect of the green parts. Of course, a lot of sustainable energy, water storage also in the underground and in other places. So there are a lot of possibilities for circularity. Also some examples of decentralized solutions, because if you have to extend the existing treatment plant or need very long sewers or tubes, then it can be interesting to have also some local treatment. Especially also for heat recovery, which is very interesting if you do that locally. So, for example, from the shower, you can directly implement in new buildings a heat exchanger to reuse the thermal energy. Next slide, please. So at the moment, as I mentioned, we are still finishing the backcasting. So that means not only making a roadmap to this future, but also looking back to the current times and then defining which kind of knowledge questions still exist, which kind of innovation needs need to be fulfilled, and especially also important, at which moments do you need to make choices. So that's also depicted in the next slide. So if you want to go to this future, and at certain times you need to make choices. So if you look backwards, you can define at which moment do you need to make a choice, and then also define which kind of knowledge question needs to be answered before you can make the choice. So that's very important, I would say. Then the next slide, nearly finished with the presentation. So a bit concluding our study about impact and opportunities for fully circular urban water cycle, focused on 2050. We delivered a sort of scorecard which can be used for defining circularity. You can compare the current situation with new concepts and the future, and then see if you score better on all aspects or if some aspects are even decreasing in the score. So that can help you to make choices. We also depicted a dot on the horizon with an inspirational drawing, which should trigger discussion and help us to move forward to a more circular and hopefully fully circular water cycle in 2050. And together with the backcasting, this should give policymakers and administrators, the responsible people, handles, tools to develop to the circularity in the near future. Next slide, please. Final slide. Yeah, with that, I would like to thank again the collaborators in the project. So the direct collaborators, but also the other people that all participated in this whole project with workshops as well, because they shared their knowledge and expertise on technologies and visions for the future, which we collected in the results that we presented in this presentation. So thank you for your attention, all of you.
Thank you, Kees, for leading us through the new system, or in how we have to think and to realize these opportunities and also these ambitions we as a society mention, and what we want to reach. Also looking at the Glasgow COP, what is it, 2021, or what is it? I see that you are bringing all characteristics in one figure, linking it to the donut economics. Also very interesting to see. And from my point of view, yeah, I think it can help the discussion on sustainability, because you make it a bit complex, understand the complexity, and then translate it into workable pieces. That's my idea about this. I see a question from Fahia Hassan, and the question is, what is the most challenging change in changing linear to a circular cycle water chain? Can you answer this question, Kees?
Yeah, there are a lot of challenges, of course. The most challenging is maybe still difficult to answer. In the end, it's the complexity, because you have to work together with a lot of organizations and people from different backgrounds. Because if you make circularity, it's usually not only one organization that can do this alone, and that makes things in general complex. So aligning and organizing the governance, at the moment I would say that's maybe the most challenging, because legislation you can change. With technology we make really nice progress, and for example censoring is very important, so that's still a challenge. But maybe the governance and how to organize this, and how to align all the different stakeholders in this water system, which is of course aligned also with other systems. The system integration, that's probably the most challenging.
Thank you. And how do you make the connection with other stakeholders outside the water sector? Because I think if you want to reach the challenges or reach the goals you mentioned, you make these steps as well.
Yeah. So for example, for our workshops, we invited also people from organizations a bit outside of the water sector. Or more general organizations like provinces and people from universities, but also from commercial companies, industries. So with that, and that needs to extend more and further with these results. We need to keep on communicating and trying to link to the other sectors to align this. And with this, I think we made some steps, but still more needs to be done to make this system change together.
Yeah. Yeah. One final question, Kees. It's from Willy van der Broek. How do you make circular systems economically viable, given that traditional inputs are presently just cheaper?
Nice question. Yeah. Although it's not always the case. So if you need water at a certain place, and actually you also produce wastewater at a local area of this water, or where you have this water need, then it can be actually economically interesting to reuse that water and not to transport it from further away. So even in the Netherlands, on the higher sandy soils, you have moments where you have little water, and if you have to pump that from a river, which is then also with low discharge flows, then it can be very interesting to reuse local water that is treated from wastewater. And there are also other examples where you have additional benefits. So for example, phosphorus recovery in the form of struvite, which is now more and more applied already. It has economically benefit because you avoid clogging and unintended precipitation of this phosphorus in pipes and pumps and other places where you have to have more maintenance and replacement. So in that sense, you have also economically viable solutions. And of course, in the general picture, I think I have to short. Also, fossil fuels and other raw materials maybe should be taxed a little bit more, because if you take everything into account with all the climate impact that these fossil materials have, then they should be much more expensive. So that's also a button to play with.
Thank you, Kees. And also when you mentioned making connection with other possibilities and make smart connections and introduce also operation and maintenance. I heard you were saying this as well. Fahir mentioned also when our region has never done it, what things should really be prepared in advance. I think Kees and Fahir, please contact each other and do this besides, or maybe in the Q&A, then you can answer these questions for yourself. And I would like to go to the next presentation, if you're okay with this. Noorhida Sharo, if I'm right. You're bringing us in the world of all palm empty fruit bunch, which is derived cellulose as a carboxyl platform for cationic dye and metal cation removal from wastewater. Nouridaya, if I'm hopefully I'll speak it in the right form to you. You are working closely together with knowledge institutes in Malaysia and Indonesia. Please introduce yourself further and show us what options you have for removal aspects from wastewater. Please go ahead.
Okay. My name is Nouridaya. I'm just on this oil the
What I see is that I cannot follow what you're saying, and Nouridaya, maybe I'm the only one who has problems to hear what you're saying, but
it's for me the same.
Okay.
So can you?
I think no, it's still not working.
Maybe without camera, your bandwidth might be better used for the sound only, and then without camera, maybe.
Yeah.
So now can you hear me?
It's still not right. Not okay. Can you close the camera? Can you switch off the camera? Is that an option? Try again, please.
Hello?
Unmute yourself and now try. See what's coming up. Well, Nouridaya, I think it's not going to work. What we can do is that we will ask the next speaker to give his presentation, that we will try again later. Is that okay for you? Then I will come back to you at 5 minutes, 11:35. Okay, then I will introduce now the next speaker, Jim Wright. Jim is speaking about the area selection for most post-hoc impact evaluation of the delegated management model of urban water service delivery in Kisumu, Kenya. I can hear myself.
Okay, can you hear me okay?
Yes. please introduce yourself, Jim. You're doing this in together with some companies in Kenya, 2 knowledge institutes I see in Kenya, and you are doing this from the UK, Southampton, I believe.
Great, thank you. So I'm in a geospatial group in University of Southampton in the UK, and I'm presenting on behalf of colleagues in Kenya, particularly JUICE, a university in Western Kenya. Next slide, please. So this is my colleague Lorna Okoto from JUICE in Western Kenya is the lead presenter of this. And what we were doing is looking at a way in which we're selecting areas to evaluate a scheme known as delegated management in Kisumu, which is Kenya's 3rd city. Next slide, please. As a very brief summary, this is part of a bigger project that brings together the ideas of water and waste management in off-grid areas. Why bring together water and waste? This is a project based in 2 countries, Ghana and Kenya. In one of those countries, Ghana, most urban households currently drink water from plastic bags. In contrast, in Kenya, the government has banned plastic bags. So the project is looking at evaluating a waste intervention in Ghana and a water intervention in Kenya. Next slide, please. So let's move on and just talk about the water intervention in Kenya, in Kisumu. So it's a particular model of delivering water services known as delegated management. That's a model that's been used in Kenya, in Tanzania, and in Mozambique as well. And as the diagram on the right shows, what happens is that a utility sets up a subcontract for the local delivery of water services, typically in a high density informal settlement. And that subcontract goes to a master operator. And then the idea is that reduces non-revenue water loss and hopefully allows some localized expansion of the service network as well, thereby improving water services. Next slide, please. So there's been quite a bit of work on the delegated management model. It's looked at things like revenue recovery and also impacts on pipeline breakages. But there hasn't actually been very much on water quality impacts of this style of service delivery. So that's our focus in the project, to look at the water quality impacts. Next slide, please. So here's a map of Kisumu on the shores of Lake Victoria in Kenya. And if you look at the graphic there, the green lines are areas that are managed directly, pipeline that infrastructure managed directly by the utility, Kawasco. And the red areas and the red lines are places where the water network has its management's been delegated, subcontracted to a master operator under this delegated management model. And so to do our evaluation, what we're interested in doing is looking at risk factors for water contamination in the built environment and seeking to select control areas that are broadly comparable for those risk factors between the red and the green areas. So, for example, in terms of sanitation provision. So there are a series of risk factors that we've tried to control for, essentially around settlement and population density, sanitation, and also the nature of the connection to the water network. Next slide, please. So what we've done here is to use a technique called coarsened exact matching that seeks, if you take small areas, enumeration areas, in effect, this statistical technique seeks to minimize differences between the green and the red areas in terms of those risk factors for contamination. And alongside that process of coarse and exact matching, what we also try and do is eliminate those areas that are simply not comparable. So, for example, rural areas and areas that are completely off the pipe water network. Next slide, please. So what we've done is to take a set of enumeration areas across the city. We've excluded some, as the top right box suggests, that are simply not comparable. The idea of a spatial spillover, by the way, there is the idea that right next to areas under delegated management, you may still see some delegated management impacts. And then what we've done is to use this statistical technique, coarse and exact matching, on the remaining enumeration areas to try and identify similar areas from both the green and red piles, those directly managed by the utility and those that are not. And in doing so, what we arrive at the very bottom of that slide is two groups of areas that it should be comparable: 139 under delegated management and 144 controls that are not. Next slide, please. This is a sort of graphic that seeks to show the way in which the characteristics of the areas are controlled for. So what we have here is, if you imagine histograms of areal risk factors for contamination, such as, for example, population density in the third row of that table, what we're seeing here is, if you imagine comparing points on the histogram, so for example, in the second column, the mean population density for the control areas versus the delegated management areas, what we're looking at here is the difference in those two characteristics. A positive number indicates that the delegated management areas have a larger figure in them. A negative number indicates it's lower. So you can see here there are fewer domestic household water meters per capita in the delegated management areas. There's a negative number in the mean column, and the population density per square kilometre is much, much higher in the delegated management areas, which is why there's a figure of nearly 10,000 in that mean column in the third row, 10,000 people per square kilometre. So this is comparing all of the areas under delegated management with all of the areas that are managed directly by the utility. And if we now move to the next slide, please. Following coarse and exact matching, what you'll see is that by selecting out a subset of those areas where we're very carefully matched on these risk factors, you can see, for example, in that third row, the population density differences between the control areas that are directly managed by the utility and then those that are under delegated management, where there's a subcontract in place. Those differences in population density have been minimized. So hopefully in doing this initial matching, what we should end up with is a more carefully controlled evaluation of delegated management subsequently. This is how the coarse and exact matching technique should work. And if we move to the next slide now, please. What we've got here is a graphic that now shows us how areas have been chosen across the city. So the coloured areas are enumeration areas, DMM in the legend, the red areas, they're under delegated management. The blue areas are controlled directly by the utility. And then those with a solid colour, the ones that are showing in pink and the ones that are showing in a solid blue, those are the ones that have been matched together with comparable characteristics for things like settlement density. The speckled dotted ones have been discarded as being too dissimilar. Next slide, please. So if you like, what we've done is to use this technique to try and improve the quality of our assessment of the impact of the scheme. So hopefully what we've done is to end up with some carefully matched areas that control for other risk factors for contamination. And then on that basis, having realised that areas under delegated management tend to be more built up, densely populated, further from main sewerage, more exposed to on-site sanitation, we should be able to sort of control for that and thereby arrive at more robust estimates of the impact of the delegated management on water quality. And then moving forward, we're now about to start in the coming month, actually, to undertake interviews with households and master operators and vendors in the city, and also alongside that undertake water quality testing, both at source, but also vended water and household water as well, for fecal indicator bacteria, E. coli, thermotolerant coliforms. So that, if you like, gives us a more robust platform for selecting those comparator areas. Perhaps the final point to make, alongside the idea of using the coarse and exact matching for impact evaluation, is that perhaps it also enables some structured decision making in thinking about places where the delegated management scheme could perhaps be extended to. So if you were thinking about extending the arrangement further, maybe this gives a sense check of the similarity of the areas that you might extend into. So on that note, I'll maybe stop speaking and hand back across to the moderator, Andre. Andre, I think you're on mute, are you?
Thank you, Jim, for giving us some insights in your work in the African region. One question I have for you is, where do you hope this project will stand in 3 years' time, let's say?
That's a good question. I would hope that I would hope that we would be able to share knowledge across the two countries is one of the key things that I would see as important. So we're due this month to have a meeting where the delegated management model, which is unknown in Ghana and not used, where Kawasco from Kenya will be speaking to colleagues in Ghana to discuss the potential of that model, including with University of Ghana. So one of the things that I would hope is that there will be dissemination of ideas between the two countries that are involved in the project.
Okay, thank you. Thank you, Jim, for your presentation. For the last minutes, I think we try again with Nouri Daya. Hopefully the connection is now better so we can understand you. Please go ahead, Nouri Daya. I'm still not hearing you very loud and clearly. No. Maybe you can switch off the video. Maybe this helps. I think this is not going to work, Nouri Daya. It's a pity because I was very interested in your research you're doing. Nuridayat, are you still there? Otherwise, I think you unfortunately will miss your presentation, but I will ask the organizers if they have an option for you, otherwise to do it in another workshop, or that we can share your presentation, because I think your subject is very useful and should be very. I think it's very inspiring as well. Well, I think we are not going to end. We are not going to make it with this presentation. Then, if you have some questions for one of the other speakers, we have a few minutes left. Please let us know. Kees, you were giving Fahir an answer on. Maybe you can share that with the audience. I don't hear you, Kees. Please unmute yourself. The question of Fahir was, when a region has never done it, what things should really be prepared in advance? Kees, you have to unmute yourself. Otherwise, I will answer your question. The answer of Kees was, Dear Fahir, thank you for the nice and relevant question. It is good to start communication with the relevant stakeholders, but also identify which materials are used and produced, so you can check if you can make them more circular. Does this answer your question enough? Cheers of Kees.
Yes, well. Sorry. And now I'm here. You can hear me. I refreshed the page because I couldn't unmute myself.
Oh, okay.
But you gave the answer already. So I hope it answers the question more or less good enough. Because communication is important. You have to speak with stakeholders. And of course, you need to know what you are dealing with. So if you make an inventory of which kind of materials you are using and which kind of materials you are producing, then you can also make the steps to circularity.
Well, thank you, Kees. I think, unfortunately, we missed the presentation of Nuridaya. Hopefully, you can share this information in another way. I would like to thank Nienke for her presentation, Kees, of course. Then Jim and Nuridaya for joining the conversation and for joining the meeting. I would like to thank the listeners to these presentations. And if you have some questions, please do this in the poll or otherwise via the organization of the Amsterdam International Water Week. Hopefully, we will see you in the coming days again. Thank you very much.
Thank you all.
Thank you.
Thank you. Bye-bye. See you.
Thank you. Bye-bye.